Hey guys, this is Daniel and welcome to a new video. We talked about 3D a lot, but as I told you last week, there are some new interests that I had and I want to talk about it a little bit different today. It actually still has quite a huge connection to 3D modeling, but it is more about the mathematics behind it. Because as an artist, you always deal with the surface of everything, you're a designer basically. You don't really understand at that point what's really going on within the computer. But to me, that question was really interesting, so I decided to work it out. And I spent quite a couple of months researching it, and this is what I recently programmed, which is basically taking coordinates for some 3D data, like I have here, and renders it as an image. And I'm going to share this link here in the description below so that you can actually take a look at the code. But I also want to give you a little bit of an introduction to this topic and how it actually works so that you also have a better idea of how Blender, for example, renders its 3D data. So it might be easier if you have a little bit of understanding of how programming works, but even if not, I'll try to cover, the general mathematics. So the first and the most important fundamental knowledge that you'll need to have in order to do anything really in computer graphics and programming is you have to know how to multiply matrices. Let me show you first how it works on one slide, but we'll not talk about this in detail yet. You just see that there is tons of matrices. This is basically a matrix, this is a matrix, this is a matrix, and these are multiplied together to get the result that we're looking for. Our input coordinate becomes, through this multiplication, the output coordinate, and this is really useful and convenient actually, because you can write it in such a compact form. So before looking at that too much, let's start reviewing or what multiplication of matrices actually looks like. This is already done, and I want to explain you how you calculate it. Basically, it's a bit hard to get used to it at first, because what you want to do is first you look at the matrix that you have, and you can say how many rows it has and how many columns it has. If I say this is a 2 by 2 matrix, yeah, it's correct, but here you say basically the number of rows first and then the number of columns. So this is a 2 by 1 matrix. And what you need to know for now is that you can only multiply matrices that have where the number of columns in the first matrix matches the number of rows in the second matrix. This is why we can actually multiply these two cases, but imagine we would flip these around, we would not be able to multiply them anymore. You can also not multiply a 2 by 2 matrix with a 3 by 3 matrix or anything else. Now let's say we have two compatible matrices. You start by looking at the first row of the first matrix and the first column of the second matrix. And then you go ahead and multiply the first entry in the first row with the first entry in the first column of the first and the second matrix. But that's not everything you have to do yet. Then you go ahead and multiply the second entry in the first row with the second entry in the first column, again of the same two matrices. And then you calculate the sum of those two results, and that gives you the 6, the first number that we'll put into this matrix. So 1 times 2 is 2, 2 times 2 is 4, 2 plus 4 is 6. Moving on to the next number, you stay in the first row because this is still the first row in the result, but now we're looking at the second column of the result. So here in this matrix, we'll now not look at the first column anymore, but at the second column. So we start multiplying. 1 times 3 is 3, and 2 times 3 is 6. So the result will be 3 plus 6, and that is 9. Then you continue with the second row this time. 4 times 2 is 8, 3 times 2 is 6, 8 plus 6 is 14, and that's your result, and so on and so on. The system is basically the same for this one, just you only have one column, so the strategy that you take is 1 times 2 is 2, 2 times 3 is 6, 6 plus 2 is 8, and then you go 4 times 2 is 8, 3 times 3 is 9, and that is 17. So this sort of calculation is a bit abstract, to be honest, for me anyways at the very beginning, because you don't really get a number as a result, you get many numbers as results, and how are these related anyways? I think it's really just a way to make multiple calculations at the same time in a structured manner. But how does this relate to coordinates and 3D data, right? That's kind of a question here. So let's look at this slide for a second. We now have a little bit of an idea what it is like to work with matrices. Basically, we have our coordinates for the 3D data, and we put it into a matrix form, like here. So x is our x-axis coordinate, y is our y-axis coordinate, and z is our z-axis coordinate. And there is this strange one that we add here below. It's not a 3x3 matrix, it's 4x4. This is because we need it actually to do all kinds of transformations, and you'll understand it in a second. For now, I just want to look at these first two matrices. What happens if we multiply these? So it's kind of complicated, but it's very easy numbers, so it's not too hard. 1 times, so basically the result, by the way, will be 4 by 1 matrix. So because you keep multiplying into kind of from right to left, we'll work our way into this direction. But yeah, we just imagine we have here, can I draw on this by chance? Yeah, I'll try to visualize that for you. If you give me a second. Okay. So let's get a marker. It should be here. Alright, so we have here, this is going to be the result. And this is now 1x plus 0y plus 0z, and then minus some variable multiplied by 1. This is why we have the 1, by the way, because that means that x will be, we basically subtract this variable from x. And what does it mean if this is a coordinate? A coordinate basically plus something or minus something, so this is our transformation or translation, along the x-axis. So any number that we will enter here will result in a new coordinate that is just x plus or minus whatever you have in that variable. It's kind of hard to write like this, but anyways, you know what I mean. This is now our new x that's going to be here. Whatever, I'll give this up. But let's leave this here. With y, something similar happens, because we now look at the next row, and we have 0 times x, 1 times y, 0 times z, and then again this variable. So our result here for the y-axis will be again y, of course, 1 times y, plus whatever we want to translate it to. And the corner will just stay 1, because we just, keep the 1 so that we can do these sort of translations and things like that. We can do something different too, actually. You see there is this 1 all the time, and this just makes sure that we keep our data preserved, basically. So if I write a 1 here, it just keeps the x in our result and adds something to it. But we can use it as a factor, actually. If you write here a 2, it will multiply our coordinate by 2, and you will get basically your coordinates scaled along the x-axis. And so only one matrix that's quite easy to understand gives you already the ability to scale your data and to translate it. And the reason why this matrix system is so awesome is because you can enter any coordinate that you want. It is not just a point that you enter here. Every single point that is in your system will run through this equation, and you will get the new coordinates. But why do we need to translate them anyways? It's basically because our camera, so you know we have a 3D space. Actually, let me open up Blender for that. I want to show you quickly how this works. Here's Blender, and imagine this is not now an image. Just imagine this is this concept of 3D space and data in it. Now, the thing is, an image is two-dimensional. So we need to sort of project our 3D data onto an image. And the way we do it is simply by eliminating one axis and using the other two for our new image. So just imagine the y-axis is the image y-axis, then the x-axis is the image y-axis. We just make the z-axis flat, so I make it 0. And I look at it from the top because now our image lines up basically, and see what we have. We have here our cube in image form, and because we have these numbers, we can simply basically output it on a two-dimensional plane. But here is one issue. This thing is still, or let's say we go back to this thing, and it's just in the center of the scene, but our camera is somewhere different. Our camera is here. The way we kind of position the camera is by starting out in the middle, and then we sort of move all our information from away from the center into sort of the camera space, and that's why we do the translations at the very beginning. And then there is let's go back to those slides. Then we have something very complicated going on here, and that is how you do rotations. That's a bit of an unfortunate thing. Even though translations and scaling are so easy, rotations turn out to be quite complicated, and it's not really that bad, but I mean, it is more of a pattern that you just have to use because this is how you rotate it. It's just a bit annoying to memorize, so just use the same matrices and it will work. You can also simplify this into one matrix, but the problem is that you will get longer and longer entries into your matrix, and it will just get more and more confusing to look at. But the thing is, if you replace these variables rod z, rod y, and rod x with your numbers in radians, by the way, in this case, you'll get your coordinates rotated around the origin. That means that basically, if you want to rotate your point by 180 degrees around the origin, you have to enter pi into this space, so it would be 3.14 and so on. Yeah, so now we have, with this we can basically position the 3D data in front of the camera so that, you know, basically with these you move your camera around. You shouldn't really think about it as moving the object, but rather moving your camera, which starts out at the center of, at the origin of your scene. But there's one last thing that is now probably the most complicated part, because the camera that you use probably has a different resolution from the units that you use in your scene. So the cube that I use in my example has the coordinates of just 1 and -1 and things like that, which means that I considered a unit to be, I don't know, let's say a unit is a meter or something. But since our camera just uses the same units initially, and the resolution of, you know, 200 by 100 would basically mean that this cube has just the size of 1 pixel, or the camera's pixel size is like 1 meter by 1 meter. It doesn't really work out well. So we have to do quite a bunch of scaling and things like that. So what this here does is basically it makes use of this camera model that I tried to visualize here. A camera has a focal length, it has a sensor size, and it has a resolution. And as I've written it here down, our f will be the focal length, which in my version, you will find different versions of this matrix, but in my calculation I keep as one variable, where others might separate it between x and y. But since I have it as one, I have two different variables for the resolution. My p x and py is basically the resolution of my picture. And then we have the sensor size. So in my case, over here, I wanted the sensor to be something small compared to, if that was a meter, I just made up something between, what is it? That would be 6 centimeters by something around 4.8 centimeters. And then there's the focal length. And you'll see that, imagine this plane was always the same size, and now you move it away. That would mean that the field of view would get narrower too. So that means how much you can see in your scene is basically the result of the ratio between the sensor size and the focal length. And the reason why we have the resolution, the amount of pixels in here too, is just to scale the whole thing up and down in order to fit, the resolution, so that 1 meter is not just a pixel, so that 1 meter can actually be whatever it is that you work with. Since this canvas, for example, has a resolution of 600 by 480, this will be my camera resolution. You might get stretching if you don't make sure that your sensor size and your, resolution line up. So I have this resolution 600 by 480, and I have matching ratio between 6 centimeters by 4.8 centimeters here. This is why it's not stretched. But play around with these variables and see for yourself what these do, if you like. Okay, but here is the last thing that we still haven't covered. Doing it this way, you get this sort of orthographic view. It does not have perspective yet. And this we cannot do straightforward with another matrix, unfortunately. Although we can, but the thing is we need to take a quick result in between. So this is now our new coordinate, which is already our camera's view, just that it doesn't have perspective. So we take it and we make a new matrix. And this matrix uses actually the z value of our result and multiplies this result here. So we have this result down here with kind of this pattern. So just save, the z value somewhere in between and then put it in here. And what this does is basically it divides x and y with the z value. So we have here a multiplication, and basically when you multiply something by 1 divided by some value, it's basically as if you would divide this first variable with this value here. So this is a division, and by dividing with the distance to the camera, this is what happens. So I'm going to scale around the center, and let's simulate what happens. So this is far away, so it will be scaled down more. So let's say I scale it down by 0.2 or 3, whatever. And now we have these points here, which are a bit closer but still a bit far away. So I will scale them down by 0.4. Then we have these points here which are already closer to the camera, so I will scale them down by 0.6. And then we have the front, which is quite close to the camera. I will scale it down by 0.8. And look at what we have here. This is actually, it's not quite accurate because I just grouped them together a little bit, but this looks like perspective already. So basically, by dividing with the distance, you get coordinates in this new 2D space that have actually perspective. So this is the last step to this system, and it produces perspective in a 3D view. And now to quickly cover the code that I have, here's some, in my JavaScript code, there's some variables at first, like the image resolution, which you want to match with this here. I have introduced one more matrix in here, which is basically the same as this. If you do it, this will be the transformation, the translation before rotation, and whatever you enter here will be the translation after the rotation from the camera's local space. So because I wanted to have the camera rotate around my cube, I don't do any initial transformations. I rotate the camera first, and then I just move the camera back by 5 units in this case. That way I always look at the center of the scene. If I would change these values, I would basically change the origin at which the camera is looking. This is basically the position relative to the origin. It's kind of a neat camera system to easily control what you're looking at. And here is our rotation, which is being updated later on. And our camera parameters, like our focal length, our sensor size. There's some, unfortunately, there are some variable names not completely lining up. Like this was called SX and SY in my slides. But looking at the matrices down there, you'll understand what it is. And here is then my 3D data. I have here some points, 8 points, and then I have some edges, which basically is information of which point is connected with which other point, 12 edges. And then down here I have, I'm calling basically this whole script that executes it. I am going through the multiplication of these matrices. I get the 3D data and I multiply the coordinates with the first matrix. I multiply the result with the next matrix, and so on and so on and so on. Here I get the result in between. I divide with the depth basically, and yeah, here is the result that I have. There is one more matrix I introduced which just makes sure that I get the right offset, because the HTML canvas has the origin here in the corner, not in the center. I kind of need to move all the results by half of the width and half of the height. And the other thing that is a little bit different from usual is that because of the HTML canvas having the y-axis going downwards and not upwards, I have somewhere here minus, just one minus that kind of flips the whole thing on its head, and I wonder if I can find it. But anyways, oh yeah, here it is, here in the offset, which basically fixes my whole setup for HTML canvas. Here is a minus before this one, which basically flips the y-axis, since we know that this one is the factor to whatever coordinate we multiply it with. And yeah, you run through all that math and you get new coordinates, which are basically x and y coordinates, and they have even a depth coordinate, but you don't really need to make use of it through rendering. And this gives you this picture. And you can imagine that in Blender and games and whatever there is as render engines, it is much more complicated, as they have to deal with what is visible and what isn't, and all the lights and shadows. There is a lot more to calculate. This is really the scratching on the surface of what you can know about this whole topic. But I thought it was interesting and I really wanted to share it and experience myself. My next goal is actually to do something in, stereography, so where you compare two images and get the 3D data out of that corresponding point on those two images. Because that basically uses the very same equation. You just have other unknowns, because in this case our unknowns were the image coordinates, but in the next project my unknowns will be the 3D points and the camera parameters, and it will be quite interesting to see how far I get. And I will definitely not get it done soon, but once I have it, I'll share it again. That's basically it. Don't forget the link to this example is in the description if you want to take a closer look at it. I'm sure that I did not do the best job at this. I could probably be done better, but I'm just starting to get more knowledge in this area. Hope you liked it. So see you again in my next video.